In this example, we're going to take the equation r equals 1 plus sine of theta from an equation in polar coordinates into an equation in rectangular coordinates. Now, I will say up front, this one is going to be a little bit more complex because they're going to take multiple steps in order to get to a point where I can replace everything with equations involving x and y. Also, this example is going to demonstrate why we would not typically want to take equations that are well defined in the polar coordinate system and always convert them into Cartesian equations. There are some that are better left in one form than the other. This is going to be an example of that, and you will see why. The equations that we can use to try to simplify this include r times cosine of theta is equal to x, r times sine of theta is equal to y, r squared is equal to x squared plus y squared, as well as tangent of theta is equal to y over x. Well, what I'm going to do first with r equals 1 plus sine of theta. Unfortunately, there is not just one operation I can do to both sides to make every term simplifiable or replaceable with equations from the rectangular coordinate system. But there is an operation that I can do that replaces or fixes two of these three terms. That would be if I took this equation and I multiplied both sides of the equation by r. If I do that, I will get r squared on the left is equal to r plus r sine of theta. Overall, this means that I can replace now r squared with something in the rectangular coordinate system using the equations on the right, as well as r sine of theta. So two of those terms I can use and work with now. But the term in the middle there, that's just r, I can't do anything with quite yet. So I am not done with manipulating this equation. What I'm going to do at this point is I am going to say, let's take all the stuff that is done, that is already in a format that I like, and I'll group them together on one side. So I'm going to subtract r sine of theta from both sides to have r squared minus r sine of theta is equal to r. This groups all the stuff that I already have done and worked with on the left side, and I just need to fix the thing on the right, which is just r. If I try to multiply both sides of this equation by r again, well, that would fix the right side, but the left side would become messed up again. Instead, what I'm going to do is I'm going to take both sides of this equation, and instead of multiplying by r, what I'm going to do is I'm going to take both sides to the second power. I will refrain from foiling or factoring through that exponent on the left side, and I'll just keep that as r squared minus r sine of theta, all taken to the power of 2, is equal to r squared. This equation, all terms now are terms that I can replace with values in the rectangular coordinate system. I can replace r squared in both instances, and I can replace r times sine of theta. So I now am at a point where I can replace this with rectangular coordinates. So let's take that equation, r squared minus r sine of theta to the second power equals r squared. And let's replace one by one. The first r squared I will replace with x squared plus y squared. r sine of theta, I will simply replace with y. And r squared, I will replace, just like before, with x squared plus y squared. This now is an equation in rectangular form, as I no longer have any terms involving r or theta. Please note, however, this is not a nice equation in rectangular coordinates. This is not one that we would typically want to graph by, say, plugging in values of x to get values of y, or vice versa. If you also particularly compare this equation to what it originally was in polar, I think that it is fair to argue that the polar equation looks simpler because there are less operations happening. All that's really going on there is sine of theta, so plug in values of theta and add 1. That gives you your value of r. This is going to be a special type of graph in polar coordinates that will later on be called a limacon or a cardioid. And when you see this visually, you will also understand why we would not want to even try to make this into a Cartesian equation.